Chapter 3 takes us back to differentiation. And when we differentiate something, what we're mainly interested in doing is finding the gradient of it. Now we can say that we're finding the gradient at any one point on the curve, or we can say we're finding the gradient of a tangent to the curve. It's the same thing in fact, but we've got some special words to describe what the function is doing at any one point on it. We can say that the function is increasing, decreasing, or stationary at any one part. Now think, before you start reading ahead here into all this technical jargon, let's just think about what we already know. F of x, if we've got some curve y equals f of x is just y, isn't it really? So it's just the y value. So if I graphed something, it's just some wavy line, and I asked you to look at this graph and describe what y is doing, it makes sense, just as we read words from left to right, to read the graph from left to right and say, well, what's it doing? Well, imagine you're moving across here, you'd say you're going up a hill, wouldn't you? So you'd say that y is increasing because the values of y that we have generally are increasing. Except for this little part here, we might say, oh, that part we're actually going downhill for a little way before we start going uphill again. And this is a flat spot here, potentially a little bit of downhill, and then we're going up. So we've already learned to sort of see when things generally look like they're climbing, going down, or climbing, or going down, or climbing. And whether there might be some flat spots along the way. I can see 3 flat spots along the way on this one. So really today we're just formalising our definitions then of these words. When is the curve going up? When is the curve going down? And when is the curve flat or horizontal? So let's let f of x be some function that we can differentiate at a particular point x equals something. We'll call it a. Well, f dash a, think about what that really means. F dash x is the gradient formula, isn't it? It's like a little recipe that helps you find the gradient. It's also called the first derivative because when you differentiate f of x, you get f dash x. So if we've got f dash x and then we've subbed in some value of x, a, could be anything, 2, 3, whatever you like, let's call it a, then if this is telling us what the gradient is at a. Now if the gradient at a is positive, we've already learnt that positive gradients are going up this way, then what we can say is that the graph must be increasing. In other words, it looks like you're going up a hill as you read from left to right at that point. Now if at that point a, x equals a, the gradient there is less than 0, then we know what that looks like. It's a negative gradient, something is going down this way. We say that the curve is decreasing there, or y is decreasing, or f of x, which is the same thing as y, is decreasing there. And if the gradient at this point x equals a is 0, well, we know that a 0 gradient is a horizontal part, isn't it? So we say that the curve is stationary, or y is stationary, or f of x is stationary at that point. Now remember, f dash a is just the gradient of the curve itself, or a tangent to the curve, at some point x equals a. So then to look at an example function here, and it doesn't even need to be one that we know the formula of, even without differentiating, just by looking at the gradients, I can tell whether a function is increasing because it will have a positive gradient there. Or if it's decreasing, it will have a negative gradient. Or if it's stationary, that means that the gradient will be 0 and it will be a flat spot. Now, don't forget that if you've drawn a tangent to a curve, let's say we draw a tangent here that just touches at f, then the gradient of that tangent is the same thing as the gradient of the curve itself, just at that point. Not to either side, but just exactly at that point. So then if I can analyse this curve and find all the points where the function is increasing, it's just anywhere where there's a positive gradient. So I can see point A and B, we're going uphill there. Now notice how it doesn't matter whether y is negative or y is positive. See, we've crossed the x-axis there between A and B. The point is the gradient is positive. So the curve is going up a hill if we imagine reading from left to right. We're also going uphill again over here at G and H. Then we're flat downhill. We're going uphill here again at L and again at O. And if we want to find all the parts where the function is decreasing, It doesn't matter which side of the x-axis it's on. We're just looking for parts where the y value is dropping. In other words, the gradient is going to be negative. So we've got points D and E. Over here we have point J, and that's it. And if we look for the spots where the curve is stationary, we want the tops of hills and the bottoms of valleys, because going from negative to a positive gradient or a positive to a negative gradient, it must, by definition, have gone through a section where the gradient was neither positive nor negative. It must have been zero, if only for a tiny point on the curve. So we can see the stationary or flat spots at C, F, I, K, M, and N. Now let's investigate what the gradient is at a bunch of different points on a curve. This example says find whether the curve f of x equals x cubed minus 12x is increasing, decreasing, or stationary at these 3 points, x equals 5, 2, or 0. Now, if we want to find out something about the gradient, the very first thing that we need to do is differentiate the curve. Now, it's written as f of x, so I'll make my first line f dash x, and I'll differentiate this x cubed by bringing the 3 down and replacing the cubed with squared, and differentiating the second part, I get minus 12. Alright, now I want to find what the gradient is when x equals 5. So really for part A, I need to find f dash 5. And that means just sub 5 in to this gradient formula wherever there's an x. Now it can be handy to show you're working like this to really remind you what it is that you're doing, because there's a way you can make a mistake here. You might accidentally say 3 5s are 15 and then square that to get 225, when what you really need to do is just square the 5 and get 25, then multiply that by 3, 75, minus 12 will give you 63. So the answer here is 63. Now, what you need to think to decide whether it's increasing, decreasing, or stationary is think about what this number means. This is a gradient of the curve at the point x equals 5. A gradient of 63 is ridiculously steep. That's a rise of 63 for a run of 1. So it's definitely a positive gradient, and we can say that we are increasing at this point, increasing rapidly. For the second one, we want f dash 2. So all the hard work's done above us here. We just need to refer back to this gradient formula and sub in 2 where they have the x there. So we get 2 squared is 4, times 3 is 12, and 12 minus 12 is 0. So if the gradient at x equals 2 is 0, then it's a stationary point. In other words, a flat spot in the curve. And investigating the last point, when x equals 0, what is the gradient? Sub in 0 for our x, and we have 0 is 0, times 3 is still 0, minus 12 is minus 12. And that's a negative gradient, which means it's going this way. So then the curve is actually decreasing at that point.